All right, you guys, so I'm just going to run through how to find angles that are inside the circle, on the circle, and outside the circle. They're basically, some of the formulas kind of overlap, but I'm going to run through this really quickly. Whoa, sorry, that won't happen. And if you need to pause it and rewind, then please do. Really quick, I'm just going to go off to the side over here. Since we're talking about angles all day today, I just want to do a little review of angles that we've already learned. So the first type of angle we learned already is a central angle. Right, and just to refresh our memory, a central angle is an angle whose vertex is at the center. Right, and he intercepts an angle. So let's say if I said this was AB. So remember, we learned that if the central angle is, let's say, 100 degrees, then the measure of the arc is also 100 degrees, right? So when the vertex is at the center of the circle, then the angles are one and the same, right? But then we learned about inscribed angles. Right, and an inscribed angle is an angle whose vertex is on the circle. And that's really the biggest distinction that we need to remember, because we're going to talk about that a lot today, right? So where the vertex is at, that's what drives all the measurements of an angles that occur in the circle or outside the circle. It's all about where the vertex is. So the vertex is on the circle. So again, I'll just call this AB. So if I told you that, let's say this was still a 100-degree arc, then we know that the measure of the inscribed angle is half of that intercepted arc. All right, and so whenever the vertex is on the circle, it's always going to be half of the intercepted arc. And the reason why I wanted to review that is because if we go back over here, we're going to learn 3 rules today. The first rule is, what if you have a tangent and a chord or a secant intersecting on the circle? And again, the whole clue to this is on the circle, right? So we're talking about, if you look at these 2 angles, I've got 2 different angles happening here. I've got angle 1 and 2, but notice they're both being created by a vertex on the circle. So his rule is actually no different than the inscribed angle rule. He's going to be exactly half the measure of his intercepted arc. So we would say the measure of angle 1 is half the measure of arc AB. Right? It's very much just like this rule that we learned last week, right? Because the vertex is on the circle. Okay? So anytime you see a vertex on the circle, I know I keep saying that over and over again, but that's really the biggest distinction, right? So I'm just going to write a little note here. Vertex on the circle. Okay, so anytime that's happening, right, it's going to be half the measure of its intercepted arc. And of course, if we wanted to, we could go ahead and write that the measure of angle 2 would be half the measure. So if this is angle 2, we know he's half the measure of, and that's going to be a major arc, of course, right? So let me get rid of all that scribbling that I did there. He would be half the measure of arc ACB or BCA, however you want to name that. Okay, so using that rule here, we are going to do a little quick question. So it says, find the measure of arc FHG. Okay, well, it's 3 letters, so it's definitely a major arc. So we're talking about this guy right here. Now, there's 2 different ways you can find it, right? Option number 1 is you can use the 76-degree angle, right? And you can double him and figure out that this arc would be 152 degrees. But that's the minor arc, right? We want the rest of it, so we could just do 360 minus that 152. Right, and that's going to give us 208 degrees. Of course, you can also work it an alternate way, right? You could obviously use the linear pair that's happening because of the tangent, and we know that this whole angle right here is 104 degrees because he's the linear pair, and then therefore his corresponding intercepted arc would be double that 104. Right, so any way you slice it, you're going to get 208 degrees. Okay. All right, so that's vertex on the circle. Okay, let's go to rule number 2. This is angles that are created by a vertex that is inside the circle. And when we say inside the circle, we're talking about not at the center. Because obviously if the vertex was at the center, then we would just be talking about an inscribed angle, and those are nice and easy because the arcs are always the same as the measure of the central angle. But what if we're talking about angles that are somewhere else, right? Inside the circle. And so you can read all that lovely verbiage up top right there in the red. It says if two chords or secants intersect inside the circle, then the measure of the angle is half the sum of the measure of the arcs intercepted by the angle, and it's vertical. All right, that's very wordy. So basically what that's saying, let's say I want to focus all my attention on angle 1. Well, we also know that I could label this angle 1, right? Because he's the vertical angle. I don't like writing my ones like that, right? He's the vertical angle, so we could also call him angle 1. In which case, the angles that I should be focusing all my attention on then are the arcs that are being intersected by the two angle 1s. Okay, so I only want to look at the arcs that are intercepted by the angles that are numbered 1. And then I know the measure, what this rule is telling me is the measure of angle 1 will be half the sum of the measures of those two arcs. So we're going to add arc AD to arc BC, and then we're going to cut that in half. So essentially it's the average. Because you're on the interior of the circle, the measure of any angle on the interior will just be the average of the two angles. Now this rule, of course, it does apply to central angles, right? Central angles would absolutely still use this rule, but we just don't need a fancy rule for central angles. But this works for any angle being created inside the circle. Now, if you wanted to find the measure of angle 2, well, then you would use the two arcs being created by the angle 2s, right? And it would be the exact same thing. Okay, so let's turn the page and just do a quick example here. We're just going to do one quick example for each rule to make sure we understand it, and then we'll do more complicated problems here in a second. All right, so we're looking for x. Well, clearly, let me use my highlighter here. X is intercepting this arc and this arc. So I know x is simply going to be the average of the two arcs that are given to me there. So we're going to add the 112, the 140. We're going to cut it in half, and that should give us 126. Okay, so it's really that easy. All right, here we go. Last one is, what about angles that whose vertex is outside the circle? So clearly you can see we've got 3 different scenarios here. The rule is actually the same for all of the scenarios. We're just going to adjust it slightly based on the problem. But the rule is exactly the same. So when we say vertex outside the circle, right, I'm talking about vertex Q. Right, that vertex is clearly outside the circle, or vertex L, right? He is clearly outside the boundaries of our circle, or vertex D, right? He is outside the circle. So anytime you see an angle being created outside the circle, you're going to use this rule. Now, like I said, it's the same rule, right? So basically, instead of finding half the sum, you're going to find half the difference of the two intercepted arcs. Now, when you're adding, order doesn't matter, right? But when you're subtracting, it does, right? So we do have to make sure that when we are finding the difference, which is the subtraction, that you always do the bigger arc minus the smaller arc, right? That should kind of, I'll write that down though. Bigger minus smaller arc. And that should be kind of common sense, right? I can't have a negative angle for a measurement outside my circle. So I have to do bigger arc minus smaller arc. Okay, so basically, here's what that's going to look like. Now, the only thing that's going to change, like I said, the formula is exactly the same. It's half the difference on all of these. But what's creating the angle is going to change things up a little bit. So I just want you to notice that this is a tangent line, and this is a secant. So in our first diagram, it's a tangent and a secant. Now, the reason why I want to know that is because anytime I'm dealing with a tangent, I need to find that point of tangency, which is happening there at point R. So my first arc is going to be going from R to S, right? And my second arc is going to be going from R to T. So when we talk about the two arcs inscribed by the angle, we're talking about the arcs that are trapped within the angle, right, between our boundary points. That could be the point of tangency, or that could be the intersection of the secant and the circle. Please notice that I don't need this part of the circle, TS. I don't need him at all because he's not bound within the angle that I'm trying to solve, right? Only the arcs bound within the angle are the ones I would care about. So when I set up this math problem, I'm going to do the measure of angle 1, which is angle Q there on the outside, is going to be half the difference of the two arcs. So we're going to start with the largest arc, which of course, the largest arc will always be the one furthest away from the angle, right? So arc RS is clearly bigger than RT. So we're going to subtract arc RT from RS and then take half of that, and that would give us our answer. Now, obviously in a second, these are all going to have numbers, and so it'll make a little bit more sense. But right now, we're just going to write those down. All right, number 2 is, again, the exact same formula, but there is a little twist here because this side of the angle is a tangent and this side of the angle is also a tangent. So do you notice how we need the arcs that are trapped inside the circle? But because it's two tangents, everybody's trapped inside the circle. The whole circle is trapped inside of the angle. So this is where it's really important, again, to find those points of tangency. So M and N are our points of tangency. So one of our arcs is going to go all the way from point of tangency to point of tangency. And then the inner arc would be MN. Okay, so when we do arc minus arc, right, you just got to find those arcs that we're actually looking for. So if I was doing this problem, I would say the measure of angle 2 is half the measure of arc MPN, right, because that's our major arc, minus the measure of arc MN, right, furthest minus closest, because it has to be biggest minus smallest. Okay, and that would be our formula that we would use to find the measure of angle 2. And then last but not least, the measure of angle 3. This one's probably the most intuitive because it's just two secants, right? So I have an angle being created on the outside from a secant and another secant. So clearly I'm only going to use the angle inscribed, right, or caught inside. Right, so I only need those two little arcs. I don't need any of that on the circle. I only need the arcs that are encompassed within the space of the angle. So we would say that the measure of angle 3 is half the difference of the measure of arc EF minus the measure, of arc GH. Okay, so notice every single formula is identical. Right, it's just a matter of what's creating those arcs. Is it tangents? Is it secants? That's it, the same formula. All right, let's go do some problems. Here we go. Number 1. All right, so the first thing we need to ask ourselves is, where is the vertex? Well, the vertex is clearly on the outside of the circle. So X is going to be, and by the way, the X is referring to this angle right here. I know it's kind of hard to tell. Is it talking about, we know it's not talking about the arc because the arc is 27. So I know my vertex is outside the circle, which means I'm going to be using half the difference formula. So X equals half the difference. Again, I know it's going to be, right, the 125 because I have to go biggest to smallest. And then minus, we're going to subtract that 27-degree arc. And there you have it. That's really all you have to do. And make sure you show this on your homework, right? I need to see that you know where the numbers go and what you're doing, and not just typing it in your calculator and just giving me the answer, right? So I at least, like, bare minimum, I want to see that formula work, and then you can just tell me what the answer is, right? So if we take half of, 98, that's going to give us 49. Okay, so I mean, you really just need to show me that. Again, it's very quick work. It's just a matter of just knowing which formula to use. Okay, all right, let's hop to number 2 here. Again, I'm noticing that my vertex is outside the circle. So I'm going to be using our formula that X equals half of the outer arc minus the inner arc. Now here's the kicker. They only gave me the inner arc. I'm just going to eyeball my points of tangency. So the 117 is like from here to here, but I clearly need all of this too because the entire circle is bound by the angle. And of course, I can figure out what that measure is because it's the full circle. So 117, I can just subtract him from 360 to figure out that this is 243 degrees left for that major arc. And now I can finish off my problem. Like, oh yeah, it's just going to be half the difference of 243 and 117. And when I do that math, it's going to give me 63. And you can put degrees if you want, but the degree symbol is already in the picture, so that's why I'm not doing that. Now you'll notice this lovely yellow box that I have here, and this is called the secret rule of tangents. I would highly suggest you know this rule because it's super handy and it takes a lot of work out for you. So basically what I'm going to do is I'm just going to draw a circle and I'm just going to draw two tangents surrounding that circle. There you go. And I'm going to label this outside angle X degrees, and I'm going to label this arc Y degrees. All right, well, if you can kind of figure that out based on the problem we just did, because we just did it the long way. I would consider it the long way on this problem. We just found out that 63 degrees was X. Well, do you notice a special relationship happening between that angle and his closest arc? 117 plus 63, that adds up to 180. And guys, it always will. As long as it's created by two tangents, this only works for tangents. It does not work for secants or anything like that, right? So in this picture, X plus Y will always add up to 180, right? And it has to be, it's only the closest arc, right? So the angle on the outside and the closest arc to him will always be supplementary. And if you remember this rule, it makes much lighter work of some of the much more complicated problems that we'll do later on, where you're not going to be given a lot of information and it might take you like 10 steps to figure out that angle. Or you could just know this secret rule and be like, oh, it's supplementary, so I could just get to my answer right away. Okay, so I'm just throwing that out there. It's definitely something that you'll want to know. Okay, all right, number 3. It looks like we have another vertex outside the circle. So again, it's just going to be the half the difference, right, of our two intercepted arcs. So 72 minus 22, obviously that's 50. So half of 50, 25. Again, nice and light work today. Just got to know your rules. All right, let's hop to just a few more examples and then we're pretty much done. Here we go. X, Y, and Z. Okay, so here we go. One thing I notice about this picture that should jump out at you right away is that this is a diameter, right? We definitely want to see that because that's going to drive pretty much all of the answers here, right? So the fact that that is a diameter means X, of course, is 180. And I also have a tangent right here. So I'm going to just eyeball his point of tangency to be right here. And Y, of course, would be the rest of the arc of the semicircle, right? So I know if 135 degrees is taken up, then that means Y has to be 45 degrees. Right? He's got to be the other 45 degrees to make the half circle. And now that we know that Y, now I can solve for Z, which is an outside angle. So I know Z is going to be half the difference of his two intercepted arcs. And his two intercepted arcs are 135 and 45. So that's going to give me half of 90, which makes him 45 also. Okay. All right, moving right along. Number 5, looking for X. Okay, well, this one's a tad bit different because my angle is on the outside of the circle, so I know I'm going to be using the 1/2 of the difference rule, but in this case, we know the angle on the outside, right? So now it's going to be 42 equals half of his two intercepted arcs. Here's my point of tangency. So x is referring to that, right? So then x minus 68. Right, so in this case, we're just kind of working the problem backwards. We're looking for one of the arcs given the angle. So same formula. And you can solve this however you'd like. I would just multiply by 2 on both sides to get rid of the fraction, which also allows me to drop the parentheses. And then I can just add that 68 to the other side, and I'm getting 152. And that looks about right. Not that it needs to look right, because a lot of your pictures are not going to be drawn to scale, but you can kind of determine that. All right, last one, very similar to this one. All right, we have a vertex outside the circle. All right, we're doing a lot of these. X, so x plus 28 is our outside angle. We know he's half the difference. So I'm going to use brackets here. You don't have to. I'm just going to, because I'm going to put that 6x minus 42 and then minus the 60. Now, you don't have to do this, of course, but you do want to be careful, and I'm pretty sure there's one of these on your homework, where I know I'm subtracting the 60 because he's the smallest arc, but you got to be careful, because if this was flip-flopped around, you'd be subtracting a binomial, right? And you always want to make sure that those minus signs are getting distributed if necessary. So that's just my 2 cents on that one. So this is our algebra equation that we're solving. Again, I'm going to go ahead and multiply by 2 on both sides to get rid of the fraction. You do not have to do it that way if you don't want to. But I'm going to go ahead and do that to give me 2x plus 56, and then I don't have any fractions anymore. And let's see, on the other side, I'm just going to be left with 6x minus 42 minus 60, so that's just minus 102. And that looks much nicer. If you want to just distribute the 1/2, you can, because everybody's an even number. You'll get the same answer, so that's fine too. Let's see, I'm going to go ahead and subtract all my x's. I'm going to subtract them to the right so I can keep them positive, but you can do whatever you'd like. And then I'm going to add my 102, so I'm going to get 158. And then I'm going to divide by 4, and I'm going to get 39.5. And voila. So there you have it, right? How to find, now these were all angles outside, so just be aware we practiced that one a lot, but don't forget about this guy, right? Angles that are inside the circle is half the sum, right? And then of course this guy, right? Angles that are on the circle are half their intercepted arc. Okay, so there are some tricky ones on your homework today, right? So you really just need to ask yourself, where's my vertex? Is it on the circle? Is it inside the circle? Or is it outside the circle? Because that's going to determine which of the 3 formulas you use. Okay? All right, you guys, let me know if you have any questions, and that's about it.